Should I begin?
Yeah.
Okay. Welcome back to the next session of Special Functions and Number Theory seminar. I'm pleased to introduce the speaker of today's seminar, Professor Murali Srinivasan from IIT Bombay. He'll be talking on a Q analog of the adjacency matrix of the NQ. Over to you, Professor.
So let me share my screen. So is my screen visible?
Not yet.
Okay. Now I think, yeah.
Yeah.
Okay. So I thank Gaurav for his kind invitation to speak in this seminar. So I'm going to speak about, this is the title. So what's it about? Okay. So it's about the four matrices. So there's Mn, Kn, KQn, and Mqn. So Mn is the adjacency matrix of the N cube. Kn is the Cox matrix, and their Q analogs, and mostly about their spectral theory. And Mn and Kn are very well-known matrices. KQn is a very interesting matrix, which is not that well-known. And MQn is what we have defined. So that's a new matrix here. And also, you could approach this from different perspectives. Markov chains, algebraic graph theory, up-down operators on posets, or Leonard pairs and orthogonal polynomials. So mostly I'll be sticking to these up-down operators, but the matrix is best defined using Markov chains. So little bit of just the definition will be by Markov chains. So we'll do that. And I will not be talking of Leonard pairs and orthogonal polynomials because my knowledge of the subject is quite limited. But it does make a crucial appearance, so I'll just mention it when it comes. But otherwise, I will not be talking about that. Okay, and let's spend... Okay, so I'll give you Kn and Mn. Those are very well known, but nevertheless, we will go through the proof. It may be obvious to some in the audience, but it will tell us what needs to be done for the Q analog. Because in the Q analog case, I may not be able to go through the details of the proof. Okay, so let's recall this random walk on the N cube. It's very well known, very classical. It's the first random walk one considers. So here is the Markov chain. So the state set is all subsets of the N set, 1 to N. And so suppose you are at state X. Then how do you move from state X? So you pick an element J from 1 to N uniformly at random. If J is not in the set X, you add it to X. So you move from X to X union J. If J belongs to X, you drop it from X. So that's a Markov chain with state set Bn. And its adjacency matrix and its transition matrix is easy to write down. So let me define this matrix Mn, which is the adjacency matrix of this N cube. So it's a Bn cross Bn matrix. So 2 to the N cross 2 to the N. And if you have row X and column Y, it's a 1 if the symmetric difference of X and Y is 1. So either X contains Y and with one more element, or X is contained in Y and Y has one more element. So this is the adjacency matrix, and your transition matrix of the random walk of this Markov chain is 1 over n times mn. Okay, so now let's if you to know how the long-term behavior of this chain, you need to know its spectrum of mn, and even eigenvectors and eigenvalues both we need to know. So let me just rewrite this in terms of up and down operators, because later it will be crucial to work in this framework. So let CBN denote the vector space with Bn as basis. So you define an operator, say U and K, where K is between 0 and n. So what it does is, it's called the up operator, the kth up operator. So you take a set X, and if the size of X is K, then you take it to sum of all those sets of size K plus 1 which contain X. And if the size of X is not K, then it's just set to 0. So it only operates on sets of size K, and other sets are set to 0. So for example, if you look at U4, 2, so n is 4 and K is equal to 2. Then if you operate on the set 1, 2, 4, since that's not of size 2, it will go to 0. But if you take the image of 1, 3, so take all subsets of size 3 of the 4 set which contain 1 and 3. So that means 1, 2, 3 and 1, sorry, this is 1, 3, 4. So there's an error here. So you either add 2 or you add 3. So that's the up operator. And similarly, you can of course define down operator. When you go down 1, you throw away one element of the set if it's of size K, otherwise it's set to 0. And then Un is, you sum over all U and K. So then you take X to the things covering X, independent of the size of X, whether it's 0, 1 or n, you take it. Similarly, down operator. So your matrix, the adjacency matrix Mn in the standard basis Bn can be represented by Un plus Dn. So any element X, any subset X will go to the elements covering it and go to the element covered by it. Sum of all those elements. That's your An of X. Okay, so that's notation for this. So here is the theorem, which is, I couldn't find I don't know the exact, when it was first proven, it is folklore. So the eigenvalues of this matrix are n minus 2k, and with multiplicity n choose k. So it has n, it's a 2 to the n matrix, so but it has only n plus 1 eigenvalues. And they are n minus 2, n minus 4 up to minus n, differing by 2 each time. And the multiplicity of n minus 2k, then choose k. So the sum of the multiplicities is exactly 2 to the n. And also an orthogonal eigenbasis of this can be written down. It's a symmetric matrix, so there is an orthogonal eigenbasis, and it can be written down explicitly. Now let us, I'll spend a few minutes on the proof. It's very well known, but let's do it. Because later I may not be able to give details. So now you take the usual inner product, but this factor 1 over 2n, that's because that's coming from the Markov chain. The stationary distribution of this chain is uniform. So you put that 1 over 2 to the n factor. That's not important. It's the standard inner product. So inner product of x and y, where x and y are sets, is 1 over 2 to the n delta xy. Now you write down, the idea is you write down the eigenvectors and then you get the eigenvalue automatically. So there are 2 to the n eigenvectors. So the nice thing here is that you can, For every set X, you can index the eigenvectors by the subsets of M. So for every X in your set Bn, you write down this vector V sub X, which is sigma over all Y in Bn minus 1 raised to X intersection Y, Y. So the support of this vector is the entire cube. So there are 2 to the n components here. So all of them have non-zero coordinates. And so these are the eigenvectors. You can see how. So let size of X be K. So then let's apply the adjacency operator An to Vx. So remember An was Un plus Dn. So this is the same as An times Vx is sigma Y minus 1 raised to X intersection Y, Y. Now, this is going to be sigma Y, Y, and then let's look at the coefficient of Y. So remember An was Un plus Dn. So every Y will either come from some set above it. So you can have a set Y union J from which you can drop J. So you'll get a Y. And Y union J would have a coefficient minus 1 raised to X intersection Y union J. So for every J not in Y, you will have a term minus 1 raised to X intersection Y union J, Y. And similarly, if a J is in Y, then you look at Y minus J, and then you add J to that. So for every J in Y, Y minus J will have a coefficient minus 1 raised to X intersection Y minus J, and that will, when you add J to Y minus J, you will get Y. So the coefficient of Y will be exactly this. Now now I claim that, let's look more into this. Now your X at size K, right? I'm assuming that X at size K. So what will happen? If that X was not, suppose take an element J which is not in X. It could be in Y or it need not be in Y. In any case, suppose that J is in X but not in Y. Then this cardinality, Y union J intersection X and X intersection Y would be the same because J is not in Y. Similarly here, this X intersection Y minus J and X intersection Y would still be same. So for every element which is not in X, there are n minus K elements not in X. All of them will give rise to a +1 sign. And conversely, if a thing is in X, then the sign of X intersection Y union J and X intersection Y would have differed. And so there will be minus K of those. For everything in X, you will get a minus K. And for everything not in X, you get N, because so many of them would give rise to +1s. And K of them will give rise to -1s. Otherwise, X intersection Y union J, you can replace the X intersection Y. So this is precisely N minus 2K times Vx. So Vx is an eigenvector with eigenvalue N minus 2K. Now, why are these independent? That's you can just calculate. You can show they are orthogonal. So let's calculate Vx inner product with Vz, which according to this formula would be 1 over 2n sigma over all y minus 1 raised to, here you'll get X intersection Y and here you'll get Z intersection Y. Now if X were Z, this is actually, these two would be same, this will be E1. So this would be non-zero. So this quantity is inner product is non-zero with X were Z. Now suppose X is not Z. So you can pick an element in one of them and not in the other. Say A is in X minus Z. It's in X and not in Z, or the other way around. It's in Z but not in X. There will always be such an element because X is not Z. And then you can pair this up like this. So once you have chosen an A, you define Y prime to be Y union A if A is not in Y. If A is in Y, you delete it. Y prime is Y minus A. Then this minus 1 raised to X intersection Y plus Z intersection Y plus minus 1 raised to X intersection Y prime plus Z intersection Y prime. These two would have opposite signs because one of the intersections would have changed the parity. And by pairing the sets into Y and Y prime, you can pair this into two things and the sum will become 0. So if X is not Z, they are orthogonal. Otherwise, they are. So this proves the theorem. So just one message to note from here is, see, we index the eigenvectors by this Bn. And of course, we could always say that there are, 2 to the n eigenvectors. So you can always index by subsets. But there's a point here is that it was not just a bookkeeping device. The indexing set was actually used in the definition of the eigenvectors and also in the proof that they are orthogonal. So the indexing set is more than a bookkeeping device. It played a role in both the defining the eigenvectors and in the proofs. So this problem is going to occur later. The same problem will recur later. We will see in what form. Okay. So that's the first chain, and now let's go to the Ehrenfest chain, which is suppose you have n indistinguishable balls which are distributed among two urns, 1 and 2. So at each step, you select a ball at random and transfer it from its current urn to the other urn. So there are n balls. So the state of the system can be the number of balls in the first urn. So let's say there are j balls in the first urn. So what is the probability? You can either, the number of balls can increase by 1 or they can decrease by 1. So if the ball selected is in your current urn, so that's the probability of j by n, right? There are n balls. So the one you select is in the urn 1. So that's j by n. So with probability j by n, it becomes j minus 1 because then it will be transferred to the other urn. Or with probability n minus j to the n, it will increase to j plus 1. So the transition matrix is 1 by n kn. So this will be the transition matrix. Right? So it's a tridiagonal matrix. Suppose let's look at the third column. Suppose there were 2 balls in urn 1. It can become 1 with probability 2 by n, and it can become 3 with probability n minus 2 by n. So 1 over n kn is the transition matrix. So kn is called the Kath's matrix. So another way to think about it is, I told you the random walk on the hypercube. So you can lump states of the same cardinality. So for instance, suppose you want to start with this, in this Ehrenfest chain, you want to start with the j balls in urn 1. So you go to the previous chain, pick a j subset with uniform probability. Then start the chain from that subset and only keep track of the cardinalities of the sets. So that you have lumped all the chains with the same cardinality into one superstate. And that chain will behave identically to this chain. So, and that's useful, we will just see this way of thinking about this. So the eigenvalues and eigenvectors of this chain, were determined by Kath in a famous paper in 1947. And he worked directly with the matrix Kn. So what he proved was, the eigenvalues are the same as in the previous case, n minus 2k. And the eigenvectors also can be written down. They are canonical because they are all distinct and you can write it down. And as I just told you, that the cards directly work with the matrix Kn. Nowadays, it's easiest is to approach it via the result I had just shown for Mn, the adjacency matrix of the cube. And we can just, it's an easy consequence. I'll just go through it. So the easiest approach is to use the result via Mn. So first we note that, let's go back here. See, since the superdiagonal and subdiagonal values are non-zero, you can easily check that each eigenspace would be one-dimensional. So what you do is, now go back to the previous Mn, and you define a vector in Bn, which is Si would be the sum of all subsets of size I. So for I between 0 and n, you define that Si. So now you take the subspace spanned by S0, S1 to Sn. So S0 is the empty, S1 would be the sum of all singletons, Si would be the sum of all I subsets. So that's the space, that's called the space of radial vectors, and its dimension is clearly n plus 1. So that's closed under An, and so that's diagonalizable, right? Because Mn is already, and this would be an invariant subspace. And you can easily check that, suppose you apply Sj. You want to apply your adjacency operator to the sum of all j sets. So each j plus 1 set will have j plus 1 j sets contained. Suppose you take a set of size j plus 1, say 1. So An Sj would be j plus 1 Sj plus 1 plus n minus j plus 1 Sj minus 1. So therefore, if you write down the matrix of this An on the radial vector, you'll precisely get the Kath's matrix. And so it follows that the eigenvalues of the Kath's matrix are n minus 2k. So that's this is not the way Kath proved it, but nowadays this is the correct way to do it. It's simple. And the eigenvectors also are easy to get. Now you can do the following. So we already wrote down the eigenvectors V sub x. For every x, every k. B and k denotes all k subsets of Bn. So that was the definition of Vx. So sigma over all x in B and k. Each Vx is sigma y minus 1 raised to x intersection y, y. Now you just exchange. So this is sigma y in Bn, and then sigma x minus 1 raised to x intersection y, y. Now, it's by symmetry, you can see that, see, for every subset y, you are going over all k subset x, and you are taking this sum. Therefore, if y and z have the same cardinality, they will have the same coefficients. Because you are just going over all subsets, all k subsets, and taking the intersection with y. And so if y and z have the same cardinality, this should not change. So in other words, this vector is radial. So you have written an eigenvector for Kn. And then of course you can get the explicit coefficients out of this. That will precisely agree with what Kath wrote down. He had followed a method using generating functions, but this is easier. Okay, so that's the preparation with Mn and Kn. And there are lots of applications which I will not talk about. This is standard material. So now we'll move to our main objects, MQN and KQN. Okay, so let me now, so I'll define MQN. It can be defined directly, but the motivation comes from some Markov chain on BQN, the set of all subspaces, which is very similar to BQN. So let me define that. So let Q be a prime power and set kq to be 1 plus q square up to q raised to k minus 1. And BQN to be the set of all subspaces of FQN. I think of FQN as column vectors. Okay. BQ and K would be set of all subspaces of dimension K. And the cardinality of BQ and K is the Q binomial coefficient NKQ. Then a complement of a subspace would be a subspace U such that the direct sum of W and U is V. So that's a complement of W in V. Okay. So all right. So so here is the Markov chain. So the state space is BQN. So that is a set of all subspaces of FQN. So suppose you are at a subspace X. So given X. So how do you move from X? So first I choose a one-dimensional subspace, P, in BQN1 uniformly at random. If this P is outside X, and then you just go to span of X union P. So dimension of X is increased by 1. Or P can be contained in X. In which case, of course, you simply can't drop P. It's, in the set, you could do that. So what you do is, so within X, you look for a complement of P. There will be several complements of P if of dimension 1 less than X. So choose one of them uniformly at random. Then you go from X to Y. So it's clearly, when Q is 1, clearly you get back the hypercube random walk. And so now, and what is the transition matrix of this chain? Okay, so let's write down the transition matrix. So is the definition clear of the chain? It's if it's you pick a one-dimensional subspace at random, uniformly at random. If it's outside your current subspace, you add it, take the span. If it is inside your current subspace, then you choose a complement within the current subspace uniformly at random and move there. Okay, so let's write down the transition matrix of this chain. So the number of complements is easy to calculate. Suppose you have a k-dimensional subspace, and then first you choose independent vectors outside the subspace. So q raised to n minus q raised to k, then q raised to n minus q raised to k plus 1 and so on. And then of course several of them will give rise to the same subspace. So you divide out by the appropriate quantity. So you'll get q raised to k into n minus k. So k-dimensional subspace has so many complements, q raised to k into n minus k. Now let's see what is the probability of moving. So suppose I have a k-dimensional subspace X, a k plus 1 dimensional subspace Y, and a k minus 1 dimensional subspace Z, with Z is where Z is contained in X and X is contained in Y. So I want to know what is the probability of moving from X to Y. So to do that, essentially, the one-dimensional subspace you choose, it should be contained in Y but not in X. So the number of subspaces of dimension 1, P, which are contained in Y and not in X is clearly q raised to k, right? Number of points of Y which are outside X. So Y has 1 plus q square up to q raised to k points. Points means one-dimensional subspace, out of which q raised to k are outside X. So if you select those, then you will move to Y. So the probability of moving from X to Y is q raised to k by nq. N sub q is the total number of one-dimensional subspaces. Now you want to move from X to Z. So how do you move from X to Z? The first the one-dimensional subspace you choose must be a complement of Z in X. So the number of complements is q raised to k minus 1 of Z in X. So you must choose one of those. Once you have chosen those, each of them will have several complements, will have q raised to k minus 1. And then from among those, you must have selected X. Sorry, you must have selected Z. So this q raised to k minus 1 and this q raised to will cancel. And so the probability of moving from X to Z would be 1 over NQ. I hope this is clear. I mean, it's a standard, straightforward calculation. So the matrix can now be written down. So to go up, if you want to go up from X to Y, where X is dimension K, that probability is q raised to K over NQ. If you want to go down from X to Z, where Z has dimension K minus 1, that is 1 over NQ. And so we can define the Q analog of the adjacency matrix as follows. It's 1 if X contains Y and Y has dimension 1 less. It is q raised to k if X is contained in Y and Y has dimension 1 more and dimension of X is k. So the transition matrix is given by MQN over 1 over NQ times MQN. And so notice that this is not, this is neither symmetric nor 0, 1. Mn was a symmetric 0, 1 matrix. This one doesn't have both those properties, but you can check, which I'll explain how that comes about. So though it's not symmetric, if you scale it, that is by a diagonal similarity, it becomes symmetric. So let DQN be a BQN cross BQN diagonal matrix with the diagonal entry in row X, column X, given by square root of q raised to k choose 2, where k is dimension X. So then you can check that DQN, MQN, DQN inverse is a symmetric matrix. So MQN is diagonalizable with real eigenvalues. Now, where does this DQN come from? That's also basic Markov chain theory, which I will not be doing here. So actually, you can check that this chain is reversible. It's easy to check that. And its stationary distribution will give you this q raised to k choose 2. So I'll just give it stationary distribution. So given a subspace X of dimension k, you define pi x to be q raised to k choose 2 by pqn, where pqn is this product of 1 plus q raised to k, where k is going from 0 to n minus 1. So if you sum over all subspaces pi x, so you will get pqn and sigma q raised to k choose 2 nkq. So by Q binomial theorem, the numerator is equal to the denominator. So this is a probability distribution. So this q raised to k choose 2 comes from the stationary distribution. And since PQN doesn't depend on k, it's not important to calculate, to show that previous result. But it's, for it to be a probability vector, you need to divide by PQN. Like just in the last case, we had 1 over 2 to the n factor for the inner product. Similarly here. So now we can reformulate it in terms of up-down operators. So if you, So the adjacency, the operator whose matrix is MQN is AQN, which will turn out to be, if I go back, I'll show you. So here, so we are thinking in terms of column vectors. So if you look at the column Y, if if X contains Y and dimension of X is one more, then its coefficient is 1. So essentially you are going up with coefficient 1. But if X is contained in Y and dimension of X is K, then the coefficient is Q raised to K. It's not 1. So in terms of the up and down operator, this is the matrix. So Un plus sigma K, Q raised to K minus 1, dnk. So, I mean, one might think that Un plus dn also is the correct Q analog, but of course, that's also an interesting operator to study, Un plus dn. But its spectral theory is quite involved. I do not know whether it's even nice. I've calculated a few using Maple. It doesn't look, these are integral. We will see the eigenvalues of this, but Un plus dn is not so nice. And I'll make a few more remarks when it comes. But this is the one which are the almost exact Q analog of An, which is what happened in the hypercube case. This one has. And if you are, without the Markov chain, it would have been difficult to think of this factor. But once you think in terms of Markov chain, which is quite natural, this is forced on you, this Q raised to K minus 1. So this is the Q analog of the adjacency matrix of the NQ. And the inner product now is XY is pi x into delta XY, where pi x is that, let me just go back one slide. So this is your pi x. So this is not the standard inner product, but Q raised to K choose 2 by PQN. So with respect to this inner product, this AQN is self-adjoint, which is just what I showed you there. That DQN, MQN, DQN inverse is symmetric. So that translates to this. So this is so now we can state our theorem, main theorem 2, main theorem 1 and main theorem 2. So let me do that. So this is almost exact Q analog of what happens for AQN. So they are integral, the eigenvalues. And remember there we had n minus 2k. So here the eigenvalues are n minus kq minus kq. So of course when q is 1, it is n minus 2k. And the multiplicity is nkq. That's the theorem 1. And theorem 2 is that there is an inductive procedure to explicitly write down a canonical eigenbasis for orthogonal eigenbasis under the inner product I just gave. This is not the standard inner product, but there is this factor of pi x. That's whenever you have a reversible Markov chain which is not, whose stationary probability is not uniform, you'll have to take that inner product. So that's what. And so we will now, of course.
Sorry, and that does degenerate to the usual inner product as q goes to 1 or something?
Yeah, when q is 1, yeah. It does. Because here that becomes the stationary distribution is uniform on the hypercube. It's not uniform here. That's the problem. Yeah. And now I'll try to give you some idea of the proof. These proofs are significantly more involved than that case. And in fact, when we first wrote down, it didn't look promising at all. How will you get this? This matrix, when we defined the Markov chain and wrote this. Where was it? I'm sorry, I forgot. Here.
Here.
This one, yeah. So Subhajit and I, we had defined it, and then we were thinking about what to do. It didn't look promising. And in fact, even to get some data is not so straightforward here if you directly try to approach it, because it's a huge matrix. number of subspaces is, it's q raised to, of the order of q raised to n square. So in the set case, we had 2 raised to n cross 2 raised to n. This is a really huge matrices. And how do you write this? You have to generate all the subspaces, and then, it's not, it was a non-starter, that idea. How to actually do it? Then we made one observation, which is that, which I will come. Yeah. So one thing is, just like in the previous case, we can try to get what happened in the set case was, if you restrict to the radial eigenvectors, radial vectors, then it turns out that your adjacency operator is closed under the, for the radial vectors, that's an invariant subspace for the adjacency operator. And that's only n plus 1 cross n plus 1 matrix. And you can hope to, at least get those eigenvalues. And also, what happened in the set case was, we got the same eigenvalues and no new eigenvalues we got, right? We got n minus 2k, and those are all the eigenvalues of the bigger matrix with more multiplicity. So maybe such a thing happens here. So the first thing then what we tried to do was, so look at the radial vectors here. That is, take the sum of, okay, so let me define it here. So remember, we deduced the spectrum of Kn from that of Mn, Kath's matrix. So here we'll reverse this. What we'll do, so first let me define the Q analog of the Kath's matrix. So let's call KQn. So it is the same idea. What you do is you take the radial subspace, that is, take S0, S1 to Sn, where Sk is sum of all subspaces of dimension k. So take these n plus 1 vectors, and then you apply your AQn to that span of those vectors. You can easily see that this is invariant under AQn. And the matrix, if you write down with respect to this basis, this is what the Q analog looks to be. It will come to be 1Q, 2Q, up to NQ. And here, n q into n minus 1, q square into n minus 2, q to the n into 1. That's all. It's not just n minus 1, and so on. We have to put these q factors. Now, this is completely straightforward. But now this is just an n plus 1 cross n plus 1. And these eigenvalues will definitely be eigenvalues of the bigger matrix, because this is an invariant subspace. And so this we could try it, this is not and you can even treat Q symbolically. So we just fed it into Maple, and we were completely surprised that the eigenvalues turned out to be n minus kq minus kq. And up to, you can try, up to 7 we did, and then we were sort of convinced that for the Kath's matrix, it is n minus kq minus kq. And if things were nice, just like in the previous case, those will be all the eigenvalues of the bigger matrix, with multiplicity is much larger. But for that, we need a proof, because here we are reversing we are not deriving KQn from MQn, but rather we are going the other way. So we need to do two things. We need to prove that the eigenvalues of KQn are in fact n minus KQ minus KQ. And moreover, when you go from KQn to MQn, you don't get more eigenvalues and the multiplicities work out. So that needs to be proved. So that was our first proof. So now, before I go to the next slide, sorry. So now there is a beautiful paper by Olga Tosicki-Todd and John Todd called Revisiting a Matrix of Markers. So in which they go back to some one-page paper of Sylvester, in which he had actually calculated some determinants. And that actually is determining the eigenvalues of the Katz's matrix. Though Sylvester, up to I think 4 or 5, he had done it. And later we learned that Katz was told about this, but then he said, no, I don't believe Sylvester had the proof or something. Sylvester doesn't say anything else. He just has this thing up to, but it's very clear that, I mean, Sylvester could have done it had he wanted. So these people, that Olga Toski-Todd and John Todd gave a full proof along those lines. And we tried to imitate that proof for KQN. It's a row and column operations on the characteristic polynomial. And you have to extend it a bit more, but somehow we managed to do it. And it takes a bit of work, but we can actually evaluate this eigenvalues of this. And so in our original version of the paper, that was what was that was written down. But later we have had some nice communication. So now we can actually state this is a result of Terwilliger actually. The eigenvalues of KQN are n minus q minus KQ. And moreover, the eigenvector, the column eigenvectors, suppose you want to write down a column eigenvector of KQN corresponding to this eigenvalue, n minus KQ minus KQ. Then the ith component is given by this basic hypergeometric series. This notation is from, I think, Gasper Rahman's book. So, and he told us that this matrix appears in his classification of tridiagonal pairs. And that's where, and there is a specific reference in our archive paper, which will give you a reference to one specific paper of Terwilliger where this is written down. But there are many other references also where you can read about tridiagonal pairs and this particular matrix, how it comes up. And another, Gaurav told me another paper of Warren Johnson, which is forthcoming, where a slight generalization of part 1 is proven. There is a more general determinant. He throws in more parameters and then evaluates that determinant. And by throwing in more parameters, the proof becomes easier than our proof, which is there in version 1 of this paper. It's much longer. So if you just want to see the determinant proof, it's best to see Johnson's paper. He has a more general one and the easier proof. And so that proves this, and I will not say more. Part 2 certainly I cannot say because I do not know that subject very well. And part 1 is what I've just, maybe we'll have to move forward, but that's the KQN. That's about KQN, and that's how I came to know that this matrix is already appearing in the literature. We did not know that when we wrote this a few weeks ago. Okay, now we have to get to how to get back to the spectrum of MQN. So that's that we use another basic result of Terwilliger on up-down operators. This, of course, I was aware of. So this, and this is a very beautiful result, which is not as well known as it should be. So, and whenever there's an algebraic problem on subspace lattices, a likely tool is going to be, I mean, I have found it useful to use this tool of Terwilliger's, which I'll explain. So, where it comes from is you think of the up operator. So, up operator on subspace, it will take any subspace X, it will increase, it will go to sum of all subspaces of one more dimension covering it. So it increases rank by 1. So if we apply it enough times, everything will go to 0. So it's a nilpotent operator, the up operator. So the question is, what is the Jordan block? How does it look like? Not just that, you want to write down the exact coefficients also which come up. So let me explain that. So what's a symmetric chain? A symmetric chain in this vector space is a set of vectors, a sequence, Vk up to Vn minus k, where Vj is non-zero homogeneous, means Vj will be a linear combination of element of subspaces of dimension j. So Vk would be a linear combination of subspace of dimension k, then k plus 1 and so on, Vk plus 1 and so on. So that's the rank of Vi is I. So it lives at dimension k, k plus 1 and so on. Then if you apply the up operator to Vi, you'll get a non-zero multiple of Vi plus 1. I mean, you can also say it is Vi plus 1, but saying this way, the final statement becomes easier. So you could actually say this should be a Jordan chain. So under Un, Vk goes to Vk plus 1, Vk plus 1 goes to Vk plus 2, up to Vn minus k, and Vn minus k goes to 0. Essentially, that's what it is. But we allow some non-zero coefficients for the final theorem to look neat. So what I'm saying is, if you apply Un to Vk, you'll get a non-zero multiple of Vi plus 1. Similarly, of Vk plus 1, and then the next, and so on. And when you apply down, you will get a non-zero multiple of the previous. So dn of Vi plus 1 would be a non-zero multiple of Vi, and so on. And dn of Vk would be 0. So that will be, and it will go from k to n minus k. So it will be symmetrically located about the middle, where k is less than or equal to n by 2. So of course, so here is the theorem. So there exists a basis, TQn, which looks like the following. So this TQn is a disjoint union of symmetric chains. So each TQn goes from some k to some n minus k, and they're all disjoint. And moreover, what are the coefficients? If you pick something which is going from k to Vn minus k, so take, say, Vu. So Un of Vu would be some multiple of Vu plus 1. So that multiple, that scalar is q raised to k u plus 1 minus kq. And similarly, when you apply dn of Vu plus 1, so it will be some multiple of Vu, and that scalar is n minus k minus u q. So that to get these coefficients, otherwise I could have. So you can. I mean, these are the way I had defined that this is a scalar multiple of the U1 of Vk. The scalar multiple of Vk plus 1 is because of the neat form of these this particular coefficient, and so there is such a basis. And so if you put q as 1, so this this will be just be u plus 1 minus k, and this will be n minus k minus u. So that should remind you of SL2C. This is up operator and down operator. And so naturally this the proof will come from, which I won't give you the details. So here is one proof sketch. So you define a third operator, Hn, which is so if you take a subspace X, so Hn of X would go to some multiple of X, where that multiple is n minus dimension xq minus dimension xq. So if X had dimension k, Hn(x) would be n minus kq minus kq. So when q is 1, it is n minus 2k. So then this the triple un, dn, and Hn satisfies this relation. And you have to analyze this with the q's. It'll look pretty much like SL2C, but you have to throw in the q's, and finally you will, if you just work it out, you will get this what I told you. And these details are in this is one previous paper of mine. This detail is there. So this is referred to. You could see the details. It's okay. Once you do this, then the main theorem one follows, because you take this such a basis, then how many will go from k, from 0 to n? 1 will go. then from 1 to n minus 1, you'll get n1q minus n0q, because the one which has gone from 0 to n would have exhausted one element from level 1. So you have to subtract off the previous. So to the number which is going from k to n minus k is nkq minus nk minus 1q. Because the previous would have been absorbed in the previous chains, so many of them. Now you observe that each of these, the chains spanned by k to n minus k, they are closed under AQN, because up and down are, from the way up of Vk is Vk plus 1 and down of Vk plus 1 is Vk, some multiple. So this is all closed and up of un minus k is 0 and down of Vk is 0. So this subspace spanned by this is closed under AQN. And its matrix is actually q raised to k times kq n minus 2k. This is the Katz's matrix times q raised to k. And for the Katz's matrix, we know the eigenvalue. So this eigenvalue would be q raised to k into kq n minus 2k, which if you work out, it will be this. And so if you sum up all the eigenvalues. So the multiples of so the eigenvalues are, if you go here, so all eigenvalues look like this, n minus iq minus iq. And then the multiplicities would be sum of this telescoping sum, which will just be njq of n minus jq minus jq. So this proves the first proof of theorem 1, which gives you the eigenvalues and the multiplicities. Now so the eigenvector. So Gaurav, how much time is remaining? Just give me a rough idea.
Professor, you can take 5 more minutes if that's
okay. 5 to okay. So I'll just
sure.
give you a basic idea and then I'll stop. So this one is now we want to write the eigenvectors of this. So we want to write and get the eigenvalues from writing down the eigenvectors. So we don't refer to theorem 1, just like in the hypercube case where we wrote down the eigenvectors and applied the matrix on that and got the eigenvalues. So similar thing we want to do here. But so the first problem we face is how do we index the eigenvectors? So, it might seem that you can just repeat it looks similar to the previous case, that for every subspace X, there is an eigenvector Vx, and with eigenvalue n minus kq, where k is dimension of X, and such that these eigenvectors form a basis. We do not know any natural way to do this. The indexing is very crucial, because so what we do here is the indexing is suggested by some other approach, which is a direct sum decomposition of the vector space, which I had worked out previously, which is based on the Goldman-Rota identity, which I'll just very, very rough because of time restriction. So let GQN would be the sum of all the Q binomials. So that's the Galois numbers, all subspaces, the number of subspaces. So the Goldman-Rota identity is this well-known identity. Maybe not so well-known also. I don't find it in some standard books, though it's a very useful thing. So GQN plus 1 is 2GQN plus Q raised to n minus 1, GQN minus 1. So when you go from n to n plus 1, in the set case, things just double, which is true here. And the second term will vanish when Q becomes 1. But there are also Q raised to n minus 1 times of n minus 1 will also appear. And of course, this is, if you want to state in terms of the Q binomial, you can, so n plus 1 Q, n plus 1 KQ is nkq plus nk minus 1 Q plus this. So this identity can be given an algebraic interpretation, which is a bit, I think, yeah, I think maybe I should, it's not a wise idea to do it now. So the basic idea was to what you do is you look at subspaces in BQN minus BQN minus 1. So you fix a hyperplane in FQN and look at subspaces not contained in that hyperplane. Call that AQN. And so you can, of course, we have this decomposition. BQN plus 1 is BQN, which is just a hyperplane. So the vector space spanned by these subspaces spanned by these plus the others, those subspaces which are not contained in that hyperplane. Now we'll further decompose this. So how do you decompose? So you take the subgroup of GLN plus 1 FQ consisting of matrices of this form. So there's the identity, and then the last row is 0, all zeros and 1, and this is the last column. Now that subgroup is, of course, which you call HN plus 1 FQ. That's isomorphic to the additive abelian group, FQN plus 1 by, if A1 to AN goes to this matrix. So here when you multiply two such matrices, it's like adding the A's. Okay. So, and then this, there is a natural action of this subgroup on these subspaces not contained in the hyperplane, because you can actually see, because of the last column, if something is not contained in the hyperplane, it won't be contained after multiplying by this matrix. And then you can, so what you do is you decompose it. And this Q raised to n minus 1 will come because there are, okay. So for every, you should take the non-trivial irreducible characters. Every irreducible character will be of degree 1. Take the non-trivial ones. So there are Q to the n irreducible characters. The one of them is trivial. So Q raised to n minus 1 will be non-trivial. So W chi will denote the isotypical component of chi, where chi is a non-trivial character in this CQAN plus 1. And W0 will denote the isotypical component of the trivial representation. So then you get this decomposition. CBQN plus CAQN plus 1, this is the trivial, isotypical component of the trivial, and then 1 for each irreducible, their isotypical components. Now you end up actually, here is the surprising thing. This behaves, that CBQN plus W0 behaves exactly like in the cube case. Like when you go from n to n plus 1, you have everything is in a set can either is contained in 1 to n or it contains n plus 1. So things just double. So that's how these two behave. But the rest is, remarkable thing happens that the rest, take some non-trivial irreducible chi and look at W chi. So this W chi will be closed under AQN plus 1, and moreover, W chi AQN plus 1 will exactly look like C BQN plus 1 Q times AQN plus 1. It's a, and there is an explicit isomorphism which will do this. So this is, this requires some proof, so I will not. So essentially, the first two terms you can copy the set case, whatever is done there, even algebraically you can copy it. And what is left over is done by induction. And since this is explicitly given, you can again use a previous thing. So ultimately, you can, so the indexing set becomes, this is how you index the eigenvectors. So you take sequences which contains either zeros or ones or these irreducible characters. And and then the statement is this. So for every such sequence, you can define a vector V alpha, which is an eigenvector with this eigenvalue, and these form an orthogonal basis of the CBQN. So I think I'll already gone over time. So there are some more things which you can see. And then there's an application to rooted spanning trees, which I'll skip. Okay, thank you. Thank you.
Thank you, Professor Srinivasan, for a very nice talk. Are there any questions?
So should I stop sharing maybe?
Yeah.
Yeah.
Any questions for Professor Srinivasan?
Sorry, I have a very stupid question. Maybe I don't know whether it is worth answering, but I'll just ask. So, you know how you can count binomial coefficient as a path? You can go steps x and y, east and north, and go from one point to another, and the number of, let's say, x and y, so string, so number of x's is the k, and the total number is n. And you can do q binomial by counting areas underneath.
Right.
So if you want to generate just one q, you just think of xy equal to qyx. So you take one east north and replace it by northeast, and that adds a q to it.
Mm-hmm.
And so if you take all the paths weighted like this, then they count the same things as k subspaces, right? So
Right.
is there some explicit back and forth between the two? It might, and maybe that might help visualize better what you're doing in some sense, because you have a path and you're just flipping one corner to go up or flipping one down to come down. So that's your first proof, which I understood, that you change one point if it's there or not there, right? So similarly here, you can take one corner, east-north corner, and then replace it by north and then east, and then that will give you a path in the next.
Yeah, I understand. See, that way of thinking is useful for enumeration. It doesn't help in the algebraic aspects of these subspaces, I think. See, I have that this Goldman rotor identity I wrote down. It has non-algebraic proofs. I mean, there is a proof with exactly what you are saying. There is a way to do that. That was worked out, I think. But that doesn't help in, see, what they do is, okay. The upshot is, I think this doesn't help in writing down the eigenvectors. I think. I mean, of course, I may be wrong. That way of thinking, it does not help in the. It really helps in enumerative questions on the Q binomial. It helps a lot. But here, I don't know how to use it. In fact, if it can be done,
can we back calculate, because Michael Schlosser has a theory where he replaces Q analogs by elliptic analogs.
Okay.
And formally, and if we can back calculate this, then you'll get some kind of elliptic, random box. It will be kind of fun. Yeah, Michael, you want to comment on that?
Yes, so that might be very interesting. Yes, one should just try it to see if anything like that can be done. Yeah, so it's very speculative now to say whether that would work, but surely one could try to refine the Q extension even further. Yeah.
This actually the Markov chain behaves very differently from the hypercube walk, because see in fact this one is similar to, see, the hypercube thing is there is some centering. When you go above once the cardinality is higher than half, then the probability of coming down is higher, right? Once you are at, but here every time it's biased towards the top because there are many more vectors outside a given subspace than inside it. So very quickly it will sort of, any random walk you perform like this will be in the top 3-4 dimensions. That's where it will be most of the time. It will come, of course, it will have to come down, but that will happen very, very rarely. So and that shows up in the, if you look at the spectral gap of the Markov chain, once we have the spectral, it's constant here. It does not, which is not true for the hypercube random walk. So the behavior is very different. Initially, our aim in developing this to get the eigenvalues, eigenvectors was to apply the spectral theory for use in Markov chain theory, to study convergence. But it does give us something. But now maybe non-vector methods are also helpful there. But this by itself is an interesting, algebraic problem to get eigenvalues and eigenvectors. It's an analog of the matrix. So that's why we separated out the two. But it behaves very differently than the hypercube walk.
Thank you.
Any other questions? Okay, if not, may I request everyone to unmute themselves and clap for the speaker.
Yeah, thank you. Nice talk.